In a review article I had published in the Journal of Physical Chemistry in 2009, I had plotted the diffusivity in zeolites, MOFs, covalent organic frameworks with characteristic pore dimensions less than 2 nanometers. I had plotted the data obtained from MD simulations for spherical gas molecules argon, methane, neon, and krypton as a function of the degree of confinement, where the degree of confinement is defined as the ratio of the molecular diameter to the characteristic pore dimension. We note that as the diameter of the gas molecule approaches the pore dimensions, the diffusivity at zero loading decreases significantly, and this decrease could be as high as 1, 2, 3, 4 orders of magnitude. So small changes in the pore dimensions has a major influence on the gas diffusivities. I'd like to pursue this topic further and ask the following questions. For spherical gas molecules, it is not too difficult to define the diameter of the molecule, but what do I do for pencil-like molecules such as CO2, nitrogen, or carbon monoxide? What do I do to determine the diffusivity of chain molecules such as hexane, heptane, decane, dodecane? What if there are other factors other than pore dimensions that are relevant? What about the pore shape? Is that relevant for the diffusivity of gas molecules within microporous crystalline adsorbents? Let's begin this discussion by looking at one class of host materials consisting of cages separated by narrow windows with dimensions less than about 4.1 angstrom. We first examine the diffusivities of gas molecules in structures that consist of cages separated by narrow windows. I have here DDR zeolite, LTA zeolite, LTA stands for Linder type A, Chabazite, TSC zeolite that consists of the largest cages, and ZIF8 that has flexible windows of 3.3 angstrom. Let's look at the window dimensions in more detail. I show here the dimensions of the window aperture for DDR zeolite, Chabazite, LTA 5A zeolite, ITQ29, TSC zeolite, and all silica LTA. We note that in nearly all cases, the windows are not precisely spherical. For example, DDR, the smallest dimension is 3.65 angstrom. The largest aperture distance is 4.37 angstrom. For Chabazite, the dimensions are slightly larger, only so slightly, 3.77 angstrom, the shortest aperture, and 4.23 angstrom being the largest aperture size, and so on. For example, LTA 5A zeolite has 4 angstrom in this direction and 4.58 angstrom in this direction. Let's examine the diffusivities of gas molecules such as methane and carbon dioxide and nitrogen in such structures. The graph on the left-hand side plots the diffusivity of methane in various cage window structures. I plot the diffusivity as a function of the minimum aperture size of the windows. We see that as the minimum aperture size decreases from 4.1 angstrom to 3.65, this point corresponds to DDR zeolite, the diffusivity decreases by 2 orders of magnitude and a little bit more than that. So the ratio of the molecular diameter to the smallest window aperture is relevant in determining the diffusivity of spherical guests. For a pencil-like molecule such as CO2, the molecule jumps lengthwise across the windows, and it is this cross-sectional dimension that is relevant. Therefore, if we look at the diffusivity of CO2 with respect to that of methane, we note that the diffusion selectivity increases by about 1.5 orders of magnitude as we go from DDR zeolite, which is this point here, to LTA all silica zeolite, which has a pore aperture of 4.1 angstrom. So for pencil-like molecules, it is not relevant to use the kinetic diameter as some kind of a mean of this dimension and this dimension, but we have to use the cross-sectional dimension because CO2 jumps lengthwise across the windows. Let us get a qualitative feel for the diffusivities of gas molecules inside cage window structures such as LTA4A zeolite that has a window aperture of 4 angstroms. We examine mixture diffusivity, a mixture of nitrogen and methane. Let's look at MD animations for nitrogen methane diffusion. We note that the pencil-like nitrogen molecule jumps lengthwise across the windows. Lengthwise. Since the cross-sectional dimension is 3.3 angstrom, that is much smaller than 3.7 angstrom for methane, nitrogen diffusivity in LTA4A zeolite is about 20 to 100 times larger than the diffusivity of methane, with the result that LTA4A zeolite can be used for kinetic separations for capture of nitrogen from natural gas streams. The absorption selectivity favors methane, but the diffusion selectivity favors nitrogen. The net result is that the diffusion selectivity overrides the absorption selectivity, and nitrogen gets preferentially absorbed within the pores. Let's now examine the diffusivities of linear alkanes in MFI zeolite. MFI stands for mobile 5. MFI consists of a set of intersecting channels, straight channels, and zigzag channels. The channel dimensions are approximately 5.5 angstrom. I plot in this graph the diffusivity as a function of the chain length. We see that with increasing chain length, the diffusivity decreases up to a carbon number of 6. But when we go from 6 to 7, the diffusivity increases. To understand this, we need to look at computational snapshots showing the conformations of normal hexane and normal heptane within the intersecting channel structures of MFI zeolite. The length of a normal hexane molecule is commensurate with the distance between the intersection sites, this one and this one. However, the normal heptane molecule has a length that is slightly longer than the distance between adjoining intersection sites. Put another way, we have a situation here for normal hexane which is commensurate in length with the distance between intersection sites. On the other hand, for normal heptane, we have incommensurate diffusion because the length of the molecule is slightly longer than the distance between adjoining intersection sites. If a gas molecule is incommensurate in its chain length, then it feels a little uncomfortable and has a tendency to be more mobile. On the other hand, if a molecule such as normal hexane is commensurate, it sits comfortably and therefore its diffusivity is lower. Have a look at my presentation on commensurate, incommensurate absorption and diffusion in zeolites and MOFs. Summarizing, the molecular size is not the only parameter. The chain length of the molecule is also an important determinant in the value of the diffusivity, and we need to also understand how that normal alkane fits within the pore framework. Is it commensurate or is it incommensurate? We now examine the quasi-elastic neutron scattering experimental data on the diffusivities of normal alkanes in LTA5A zeolite. LTA stands for Linde type A. What's interesting to note is the diffusivity varies in a non-monotonic manner with increasing chain length. The diffusivity for normal octane NC8 is lower than the diffusivity of dodecane and also NC13. To understand the minimum here for NC8, let's look at the computational snapshots showing the conformations of NC8 and NC13 within the cage window structures of LTA5A zeolite. NC8 has a chain length that allows two molecules to locate within a single cage. See, we have two molecules here, two molecules here, two molecules here, two molecules here. However, NC13 has a chain length that is significantly longer and has to occupy two cages here. So the one NC13 molecule is distributed between two cages. So we have a scenario here where we have two snakes in one basket. Here we have a scenario where we have one snake in two baskets. So a cage volume is commensurate with the length of two snakes. In this case, for NC13, the length of the snake, which is NC13, is too long to accommodate within a single cage, and it divides itself between two cages. So we have a situation in which we have a commensurate occupation of the baskets. Here we have incommensurate occupation of baskets. Incommensurate occupation of the guest molecules results in higher diffusivities. Let's examine the diffusivities of normal alkanes in cobalt formate that consists of zigzag channels that are one-dimensional. This is the length of one segment. This is the second segment. A propane molecule has a length that is commensurate with the segment lengths, and it sets comfortably. And if we look at the diffusivity data as a function of chain length, the diffusivity data are shown by these green squares. We see that going from methane, ethane to propane, propane has the lowest diffusivity value, and then butane is larger in diffusivity than propane. To understand the minimum in propane diffusivity, we have to realize that propane has a length that is commensurate with the channel segment. So it sits comfortably, snugly within a channel segment. Normal pentane has a length that is longer, and the length of a normal pentane molecule is larger than that of a single segment. So NC5 is incommensurate with respect to the length of one segment. That explains the higher diffusivity of NC5 with respect to propane. If we then increase the chain length further and look at normal hexane has a length that is commensurate with the length of two segments. So here we have again a scenario for commensurate diffusion of normal hexane. In this case, the hexane molecule is commensurate with two segment lengths. Therefore, the non-monotonic behavior of the diffusivity with respect to chain length can be understood in terms of the snugness of it within a channel segment, the commensurate, incommensurate nature or between the length of the molecule and the length of a single segment or two segments. For further details, have a look at my publication of 2017 and also watch the video on commensurate, incommensurate absorption and diffusion in zeolites and MOFs. The separation of mixtures of ethene and ethane is important in the context of preparing C2H4 feedstocks to the polymerization reactor. A very promising material for the separation is UTSA280, described in this paper published in Nature Materials in 2018. The pore structure has been created or designed to cleverly distinguish between C2H4, which is a two-dimensional molecule, and C2H6 that has truly three-dimensional character. The two-dimensional C2H4 molecule can fit snugly within the pores, one-dimensional channels of UTSA280, whereas this pore shape and pore size is such as to exclude the ingress of C2H6. So the separation is on the basis of differences in shapes. We have two-dimensional C2H4 and three-dimensional C2H6, and tailoring the pore structure such that the two-dimensional molecules can enter, whereas the three-dimensional C2H6 is virtually excluded. This kind of exclusion has benefits in pressure swing adsorption technology for preparing feedstocks for the polymerization reactor. Watch my presentation on 99.95% plus pure C2H4 with MOFs ? This is available on my YouTube channel. Let's look at the separation of xylene isomers using AFI zeolite. AFI zeolite consists of 1D channels that has a corrugated shape. The distance here is 8.4 angstrom and the distance here is 7.3 angstrom. Orthoxylene molecule has a structure that can locate very nicely within these grooves in a face-to-face stacking similar to the potato chips in a Pringles basket. So we have face-to-face Pringles-like stacking of orthoxylene. Metaxylene and paraxylene cannot locate in the same manner, and they have a much longer footprint within the one-dimensional channel. I raise the question now, since the orthoxylene fits snugly here, does it imply that orthoxylene has the lowest mobility of these three isomers? I'm not aware of any diffusivity data to back up this hunch of mine, but I'll leave that as a thought-provoking question to interested viewers. And let's summarize the major takeaways from this presentation on diffusivity in micropores and pore confinement. I draw inspiration from the Dutch graphic artist Maurits Cornelis Escher. He was a genius in using both positive space and negative space when making his drawings. For example, if you look at the drawing on the right, you could ask yourself, is it a fish? Is it a bird? If you look at the positive space here, it's a fish, but the negative space is a bird. If you look at the top half, the positive space is a bird. The negative space is fish-like in character. Let's look at the drawing on the left-hand side. If you look at the positive space, the horseman is galloping merrily from left to right. If we look at the negative space, the same horseman is galloping equally merrily from right to left. So the message is, when we have the task of understanding diffusivities of gas molecules within microporous crystalline materials, we should not just focus on the size, shape, dimensions of the gas molecule, but equally we should understand the pore size, pore shape, pore topology of the host material. It's the combination of an understanding of the positive space occupied by the guests and the negative space that allows the gas molecules to locate within the pore framework. The combination would lead to an understanding of the diffusion phenomena in microporous crystalline materials.